This talk is about gyromagnetic ratios in wurtzite and cubic semiconductors. It talks about the basic physics of uh, gyromagnetic ratio and the response of the electron and hole spins to magnetic fields in these semiconductors. It covers multi-valley physics and renormalization in these materials by C. Jant Prahara's band photonics materials. This slide, we look at the basic wurtzite crystal structure of some wurtzite semiconductors. So this shows very schematically the gallium nitride crystal structure, and you can see that each gallium atom here has 4 bonds with nitrogen atoms. Now these look like tetrahedral bondings, but they're not exact tetrahedra. So in these wurtzite semiconductors like gallium nitride, indium nitride, and aluminum nitride, the bonds are a bit deformed from the exact tetrahedron. So there is, for example, if you look at this, the gallium atom here, there is a vertical bond to a nitrogen atom, and then there are 3 bonds to nitrogen atoms which are at angles to the vertical. And in the wurtzite crystal structure, it turns out usually, so this vertical bond has a different length from the bonds that are at angles to the vertical, and that makes it, it gives it a wurtzite structure. In the cubic crystal structure, the bonding has exact tetrahedral symmetry, so that the 4 bonds are of equal length and have the exact tetrahedral bond angles. So in the wurtzite structure, as you can see, as I mentioned, the bond lengths are different along the vertical direction and at angles to the vertical, and that also distorts the angle from the exact tetrahedral angle. So it's not the exact tetrahedral angle that you find in the wurtzite crystal structure. Rather, what you find is something close to the tetrahedral angles, but distorted from it. And you'll see that, for example, in these crystal structures, this is responsible for spontaneous polarization in these materials. We are not so much concerned about that in this talk, but there is piezoelectric polarization, and then there is strain. And the strain effect is affected. The strain along the different axes are affected by these bonding configurations, and the strain can and does affect the gyromagnetic ratio in these materials. And the quantum mechanical wave functions reflect these specific crystal symmetries. And so this distortion from the tetrahedral angle is responsible for a lot of the different physics of Bloch electrons in these materials. This slide, we basically move to what is called the K.P method in semiconductors with spin-orbit interaction. So here show a Hamiltonian. So there is a Hamiltonian H0, which is Hamiltonian without the spin-orbit interaction, and that basically has a kinetic energy term and a potential term. This potential has the symmetry of the crystal lattice, so it has the periodicity of the crystal lattice. So, and that gives rise to Bloch bands in these materials. And then we have this spin-orbit term, which basically is relativistic in origin. So in the rest frame of the electron, there is the electron sees a magnetic field, because if the electron it has momentum, with respect to the crystal lattice, then the electric field produced by the crystal lattice gets transformed relativistically to a magnetic field. And then the spin of the electron has associated with it an intrinsic magnetic moment, and that can couple with the this magnetic field that the electron sees in its rest frame. And that basically gives rise to this where the dot product of the magnetic moment of the electron with the relativistic magnetic field in the rest frame of the electron. And this sigma here is basically is basically a three-component thing with the Pauli matrices sigma x, sigma y, and sigma z, which basically represent the three components of the intrinsic the spin angular momentum of the electron. And these matrices act on these up, which is 1, 0, or down, which is 0, 1 states. So we have basically this doublet thing due to the spin. So you have the spatial part, but then there are two copies of it because there is this internal coordinate of the spin. So this is the full Hamiltonian that one has to solve. So one is there is the global band structure over the entire relevance zone. And then there is the corrections due to this spin orbit coupling term. But we are interested in figuring out the gyromagnetic ratio is solving these band structures in great detail near the valence band maxima and conduction band minima in these different semiconductors. And we'll move to that, we'll see that in later slides. In this slide, we basically, what we do is we look at the K.P method in greater detail. So what we do is we apply that Hamiltonian that we showed in the previous slide to the Bloch wave function of the electron. So the Bloch wave function is the product of a plane wave part multiplied by a cell periodic part. So it's basically a plane wave modulated by the cell periodic. And so you can basically apply that Hamiltonian to the Bloch wave function and then take out the plane wave part and see what the equation looks like purely in terms of the cell periodic part. This N here is the band index. So you have different bands and you have kind of, for example, different valence bands, then a conduction band, higher conduction bands, and so on and so forth. And with K is the crystal momentum, which is a good quantum number in the for the H0 Hamiltonian. And this is what the Hamiltonian looks like when it acts on the cell periodic part. So you have the kinetic energy part, the crystal potential part. But then you have this K.P term, and that gives rise to this name K.P method. And then the spin orbit term gives rise to two different terms when you write it in terms of the cell periodic part. And this is what you have to solve to get the band structure in detail close to the band extrema, at the valence band maxima and the conduction band minima. And then the further simplification can be made because these two terms associated with the spin orbit coupling, the second term can be shown to be much smaller compared to the first term, the expectation value of that. And so we can basically ignore that and write this approximate thing, which is in the second line here. So that is the K.P Hamiltonian with spin orbit interaction that we need to solve close to the band maxima and band minima in order to get the gyromagnetic ratio. And here it shows, for example, 6 bases for the valence band. So you have the orbital angular momentum and the spin angular momentum adding up. And for example, you can have the total angular momentum is 3/2 for some of these bands. And then with the total angular momentum 3/2, you can have the z component of the angular momentum can be 3/2, half, minus half, and minus 3/2. And then you have total angular momentum can be half. And then you have the z angular momentum can be half or minus half. So you can use this as the basis for the valence band part. And similarly, there are two for the conduction band part, which tends to be S-type in many materials. This is for materials like gallium nitride, indium nitride, and aluminum nitride, and also the arsenides, etc., where the valence band tends to be P-type for the orbital part, and the conduction band tends to be S-type. Now, if you go to different other semiconductors, you can have other kinds of orbitals coming in and different kinds of angular momentum structure. So this slide shows the basic Hamiltonian that results when you write down Hamiltonian in this basis. So for the valence band part, and you have two for the conduction band part. So when you use Lorenz-perturbation theory with two groups, and then you get this so-called Luttinger-Cone Hamiltonian, and you have these different terms, and these different terms are defined in terms of kx, ky, and kz. So this kx, ky, and kz appear in all these terms in the Hamiltonian, and then you diagonalize it to get the eigenstates at the band dispersions close to the valence band maxima. And then similarly, you can do it for the conduction band minimum as well. And you can get the band dispersions close to that. And so this thing is what it looks without the spin-orbit interaction. And then you add the spin-orbit interaction, and that has a unit matrix, for example, need to add this spin-orbit term to that. The wurtzite semiconductors, so this is how it looks for the, there is also a conduction band part. This is how it looks for the cubic semiconductors. For the wurtzite semiconductors, you see this 8-band K dot P model. So, and you have the, there's an 8x8 H1 part, and then there is a strain part, which can be added to this. And you again have the definitions of these various matrix elements in terms of, which have this kx, ky, and kz, and that's what gives rise to these band dispersions. So then you diagonalize this and you solve, and you get the detailed band dispersions. We'll next move on to the magnetic field, and this is where we see the origin of the gyromagnetic ratio, because usually when you apply magnetic field to any material, there is a paramagnetic response and a diamagnetic response, and you have to see which is bigger and which is smaller. You have the usual K dot P Hamiltonian plus the spin orbit part. Then you add a perturbation due to the magnetic field. And the perturbation due to the magnetic field basically looks like this, and you have a coupling with the magnetic field, which is a paramagnetic coupling, which has the orbital angular momentum plus twice the spinor angular momentum dotted with the magnetic field. And then you have a term in A square, which gives rise to the diamagnetic response. So typically, for small magnetic fields, the paramagnetic response can dominate, and that's where we get the gyromagnetic ratio part. And now the second line shows that the term multiplying the spin angular momentum is modified from 2 to 2 plus delta, and the delta is due to QED correction terms from summation of loop Feynman diagrams for scattering from a vector potential. And this is due to virtual photons in the full quantum electrodynamics picture. And that has been calculated with great accuracy, and you can use it to compare with experiments. And that can be electron nuclear double resonance, NMR kind of picture when experiments are done to determine the gyromagnetic ratio. You use this K dot P with the magnetic field dependent perturbation part, and you can calculate the splittings of the different states of the valence band states and the conduction band states close to, so this basically, the valence band states we can think in terms of holes, and then the electrons in the conduction band, and you can talk in terms of gyromagnetic ratio of holes and electrons. So basically those splittings can then be converted into an effective gyromagnetic ratio, which the electron sees in these magnetic fields. Conclusion, we have QCD and QED type corrections, which are affected by the photon spectrum in this spectra in the solid with frequency dependent complex dielectric constant. So on top of the usual QED type corrections, you have this solid has its own frequency dependent dielectric constant, and the photon spectrum is modified, and that gives rise to some further corrections. Now, the K-dot peak perturbation theory with nearest band interactions gives the gyromagnetic ratios to various orders. So I should mention here that when you solve this for the various bands, you can, for example, focus on the valence band and get the splitting, but there are corrections due to the nearest band, which can be the conduction band. And for the conduction band, the nearest bands are the 6 valence bands, and those give rise to further correction terms. So there is the first order terms for the gyromagnetic ratio, and then there are the correction terms for the gyromagnetic ratio, and that gives the full gyromagnetic ratio. Sometimes the correction terms can be significant. And then temperature can lead to detectable changes in semi-metallic systems and for certain ranges of band gaps. So if you have a small, for example, for certain ranges of band gaps, you can differentiate between large band gaps and small band gaps materials in terms of temperature dependence. Then you can have band crossings, which can lead to averaging effects for the effective gyromagnetic ratio. And the many-body correlations can change the gyromagnetic ratio due to 2D electron gas and 1D electron gas charging. So let me talk about it a little bit more. So basically, you have this Hamiltonian being solved, and then, but if you have a 2D electron gases or 2D or 1D electron gases or 2D whole gases and 1D whole gases, and there is a large density where there is significant Coulomb effects because it becomes charged non-neutral locally, then you can have further effects, and you can have many-body correlation effects. And that can change the overall response to the magnetic field and can affect the gyromagnetic ratio as well. So that covers the basic physics of gyromagnetic ratios in wurtzite and cubic semiconductors with multi-value physics and renormalization. Thanks.